All right, folks. Thank you. Let us try to keep our timetable reasonably close to what it was supposed to be. Thank you, everyone, for all these great discussions. And this afternoon, we have Katarzyna Gorska. She's currently the head of the Department of Mathematical Physics at the Institute of Nuclear Physics at the Polish Academy of Sciences, working on fractional dynamics and stochastic processes. She did her PhD at Nicholas Copernicus University under Adam Makowski, and then did a PhD at Université Pierre Marie Curie and at Université in Sao Paulo. And she will now tell us about anomalous diffusion.
Thank you very much. It is a pleasure to be here. Oh, can you hear me right now? Right now?
Yeah.
Okay. Thank you very much for inviting me, and it is a pleasure to be here. My talk will be the very simple version and related with the talk of Urna Basu. Her talk was excellent, but I will try to explain something, say something more about the Langevin equation and Fokker-Planck equation in the very simple way related to it. I will be talking about the anomalous diffusion because her talk was related with diffusion, actually. So it is the outline. I will start with normal diffusion. Normal diffusion, I mentioned about the Brownian motion, Langevin equation, which are related, it's just another description of it. And I will show you the anomalous, what it is the anomalous diffusion, in which way we understand, because it's related with the non-locality in space or in time or in space and time, but I will concentrate on non-locality in time. So it is related with the memory function. When we say about the memory functions, we should mention about the Sonin pair. Like here, we obtained some condition on Sonin page, so I will mention about these conditions. And I will mention here about the general fractional, integral general fractional derivative. But don't scare the word fractional. It means that I will consider the differential, integral differential operator, just this. And if the time allow me, I will say about the evolution. So integral decomposition and subordination. Integral decomposition is something normal which we are using. Some of us are using for the smooth functions. And if the time allow, I will say about the evolution operator approach for subordination and the generalized Catania-Vernet equation. I used here the Catania-Vernet equation. And it is exactly, it looks like the telegrapher equation. Just in telegrapher equation, we have some parameter. And the interpretation of this parameter is different. And we assume something different from the conditions. So telegrapher equation is more wider than this one. Okay, what is the diffusion? Very simple. And in high school, we are learning, we are making such experiment. We have a glass of water and put it inside the drop of ink. And after some time, yeah, we observe that this ink is everywhere. So this is the diffusion, actually. So it is a process, spontaneous spreading of particles or energy in a given medium. This medium can be the gas, liquid, or solid, resulting from collisions between the particles of these inks and the particles of surrounding liquid, gas, or solids. And when we say about the diffusion, we should mention about the Robert Brown, who first discovered this effect. He observed the pollen grains Claqueria pulchera, which was surrounded in the water. So this red circle ball is our grains, and they made the collision with the particle of water. And using the 80 years, people don't understand this phenomena. And this phenomena was explained by these guys. And it is the Adolf Fick who gave the diffusion equation, who introduced the diffusion equation, Albert Einstein, Paul Langevin, and Marian Smoluchowski. He was the Polish. I'm Polish, so I mentioned him. Just simple. And what it is interesting about the Paul Langevin, that he was lover of Maria Curie Skłodowska. So this is really interesting. Here is the equation of Langevin. So what we have, it is the very, very nice equation because it's Newton's second law where we add the external force. And here we have the deterministic external force and the random external force. And here we have noise. This coefficient here is the mass and the acceleration of the particle. It's a damping coefficient and the velocity. It's external force. And Urna used the here is related with the derivative of potential energy, and she used the oscillator energy here, such that she has the first derivative of the x square, so she has x. And here we take the white noise, and white noise is mean value of white noise is 0. And this is the diffusion dissipation theory, and it is related with the delta, Dirac delta distribution. White noise looks like that, so it is the noise. And when we, in the previous radio, when we switch off the radio, we heard such noise, and it was mostly white noise. So this. When we consider the over damped limit, it means that mass over the can you hear me? Not very well. Hello? Can you hear me? I don't know what happened. Oh.
Yeah, just to the.
And here, is it better? Oops, sorry. Yeah. Me. Is it good right now? I will try to speak. I will try to speak like that. Okay, so when we take the overdamped limit, like here, so the term with acceleration there disappeared, and we have only the term related with the velocity. And the velocity is given by the deterministic external force, which is related with the derivative of potential energy and diffusion coefficient. Diffusion coefficient can depend on time and x. And here I will say only about the dependence on x. And we want to find the x. X is trajectory of our particle. what we are doing, we are calculating, we are integrating it from t to t plus delta t. It's the time first is t and after that t plus delta t. So with this term, calculating this integral is not a problem. We can do it. Why? Because we have this force. The problematic term is this one. Why? Because we have the noise and the functions which depend on x. And what we are doing, we are assuming that such term, such integral, is given by the square root of diffusion coefficients which depend on such arguments. And what it means, such argument. Here we have the parameter alpha. And this alpha takes it's called the stochastic interpretation parameter, and it's from 0 to 1. In Langevin equation, and in Langevin equation, we have very known three kinds of interpretation, where alpha is equal to 0, is related with Hangi-Kilmatovich interpretation, alpha equals to 1, Stratonovich interpretation, 1/2, Stratonovich interpretation, and alpha equals to 1, Ito interpretation. And these things and interpretation as related with such calculation of integral. Because usually when we calculate the integral, we want to calculate the field over some curve. So here, where we have the square root of some curve, we want to calculate the integral over it. So it is related with, I think, that the Roller theorem of calculating, very simple one, of calculating the integral. So you can approximate in alpha equals to 1 that this point, and it will be the rectangle like that. With that point is Ito interpretation, it's alpha equals to 1, or you can take it half. It's Stratonovich interpretation, and usually the people are using this interpretation. So when we have the trajectory, we can calculate the probability of them. And it means that when we consider the different time, we can observe this trajectory, and waiting time distribution we can calculate, and we obtain the distribution functions, density distribution functions. And here is the first question: what will be when in Langevin equation, instead of the white noise, we are using the different noise, colored noise, and the dichotomic noise, especially the dichotomic noise. And what kind of distribution is related with it? So here, when we take the constant diffusion coefficient, we can also describe the diffusion process and its Fick approach. So we can use two equations, the continuity equations, which looks like that the changes at time of concentration is equal to the minus divergence of J of the flux, and we assume that X depend on real axis and T just is larger than 0. And the Fick law, Orna said about the Fourier law, it looks it is exactly the same, but the Fourier law we are talking when we said about the temperature, and here about the diffusion. It's a Fick law. Here is a diffusion coefficient. So flux is equal to minus T, and gradient of the concentration. And we can from both of these equations, when we join, we obtain the diffusion equation. And this diffusion equation it's for us very simple, and it's a simplest version of the Fokker-Planck equation. And we can solve it. For us, it's a partial differential equation which can be solved. So we need the we need the initial and boundary condition. As an initial condition, we assume the fundamental initial conditions is like that. And in the boundary, we assume that our concentration disappear at infinity, plus minus infinity. And what we obtained the Gaussian. And what we know from Gaussian, that the first moment, mean value disappear, and the second moment is proportional to t. Yeah. But in really world, when we measure the second moment, we observed that the behavior of the second moment is not t, is just t to some power nu, and this nu is larger than 0. When nu is from 0 to 1, we have the subdiffusion. Nu between 1 and 2, we have super diffusion, and here we have the ballistic motion. So in the very simplest way, what we can do, we have the particle position vector at x on t, and in next moment. And we can calculate the particle displacement vector. And using the cosine theorem and these things, we can find the correlation functions between the position vector and the displacement vector. And what we obtained that when we have diffusion, nu is equals to 1, there is no correlation. And if the anomalous diffusion exists, it is different than 0. And here are the first experiment in which the people observed is related with the searching of food but by some animals. And it's a spider monkey, it's albatross and chacal. But I will not concentrate on the experiment. So we have anomalous diffusion, and the anomalous diffusion can be also found by joining together the continuity equation and the constitutive relation. And in general form, flux has such form. And here we have the integral and some kernel. And this kernel, here we have x minus x prime t minus t prime. And if is a product of two delta functions, we have normal diffusion. But it is not necessary. We can use here another functions which depend on x. And if we use the power functions, we have a Levy flights, and we obtain the such equations. Here is a fractional derivative. So it means only that we have the integral representation of it. And when we calculate the second moment, so mean square displacement, it don't exist. So we are calculating another things. And with such non-locality in space, we can use also the heterogeneous diffusion in heterogeneous media. So here we have a difference depends on x. So it's x to the power minus 1 over alpha. And alpha say us about interpretation, because interpretation, three kinds of interpretation we can use only when the diffusion coefficients depend on x. Usually the people are assuming that we have absolute values of x to some power 2 minus 2 divided by beta, and beta is smaller than 2, and it's related with the crowded system. One crowded system is it's very simple to imagine behaving of the people who were in São Paulo at the underground. So in some time they stuck because it's such crowded that nobody can go inside. Or also the bacteria of E. coli behave like that. Here it's red things which are also stuck in another proteins. So when we find the Langevin equation for such Fokker-Planck equation, we obtained that they are related with Bessel process, and here we have the external force, and this external force is related with potential, and potential is logarithmic potential, which have some coefficients, and it's stochastic interpretation and beta from 0 to 1, and beta smaller than 2. And it can be repulsive or attractive. But we can also consider non-locality in time. So we have the memory functions, and here we assume that we are changing. We have power law at time, and we can also obtain the diffusion coefficients. Here is a fractional derivative and calculate the mean square displacement. And it is for the subdiffusion, it is smaller than diffusion. And for the super diffusion, it is larger than diffusion. And here, for the subdiffusion, we can find the random walk model which explained us, but for the super diffusion, we cannot find it. Nevertheless, we observe it, such kind of diffusion. And here is one remark that 1 beta is equal to 2. We have the wave equation. Okay, and here is fractional derivative, because it's not necessary to use the power law time functions. We can use another functions. And here we have the functions m and k. And usually in the literature, when you are searching reading the articles, you can find that the diffusion process, anomalous diffusion process, can be described on that or that way. But we would like to obtain the same results for from both of these equations. So we should assume something on our integral kernel on n and k. And what we assume that they satisfy the Sonin equation. What it means, Sonin equation? Sonin equation is nothing else that we say that the Laplace convolution of these two kernels are equal to 1. And we can calculate. Sometimes the people consider that the Laplace transform version, hat is the Laplace transform of them is 1 over s. But here we should pay attention that there is a problem at 0. Because when we calculate the inverse Laplace transform of it, we obtain the 0 here, the behavior of m at 0. So what it is the Sonin here is the Sonin, Nikolai Sonin. And what it is the Sonin function, Sonin pair? Sonin functions is the functions which is is integrable at 0. And it has the integrable singularity at 0. This is the Sonin functions. And if one of these functions is regular at 0, then k is distribution. So I don't know if it is related with Sylvia question, but because Sylvia asked about the noise is distribution. I don't know if noise, but when we say about the memory functions, it should be singularity distribution, singular integrability at 0. And example given by Sonin from 1884, it's related with Bessel functions. So we have the singularity in both of them. and it's a positive functions related with modified Bessel functions. And here we have Bessel functions, but we have the negative part, and we don't want this. Another example of Sonin pair is related with the fractional derivative in Caputo sense. So it is the power law, M and K, and also the distributed derivative. It's given like that. And the counter example, I call it, it is Caputo-Fabrizio derivative, where you have here is a regularity at 0 and the distribution. Okay, but there also exists another approach for solving the differential equation, integral differential equation, and the question is if it is the Cauchy problem. And it was addressed by the Kochubey, and he answered on the question. And he assumed that our functions, our kernel memory function, to satisfy such conditions, its Laplace transform should satisfy such conditions. So it means only that we should call later the padding memory, and the functions should behave like that. So it should goes to infinity. It should have the integrable singularity and goes to 0. Okay, and when we say about this, we should say about the general integral and the general derivative. So general integral is defined like that, and the general derivative it's given here. We have two kinds of the inverse Laplace transforms because it's dependent on K or M. And what we can do, we can find that in Soviet Union literature exists the Efros theorem. And what it is, the Efros theorem? Efros theorem assumes that we have two functions which are analytic functions, and we can introduce the function h. As these functions h, their Laplace transform exist, and exist another functions whose Laplace transform is given by these two analytic functions. It has such a form. And theorem says that such combination of the function g and h when we substitute q is equal to the Laplace transform of such integral. We can invert it and we obtain such a form. What we know about the Efros? Efros is a very mysterious person because he published only one article and one book, which I found. Here is a book written by him. He lives in Kharkov in 1937, 1935. It's the 30s years. And at that time was Bolshevik time. And information about the Efros theorem can be found only in the few papers. It is the paper of, is a book of graph. At that time, my supervisor, Penson, Appelblad and Mainardi. And before the First World War, he disappeared. He didn't publish anymore. So here is the Efros theorem, and Efros theorem can be related with the integral decomposition. And it is nothing strange that the functions can be splitted, can be present, a smooth function can be present as an integral of some two functions. So these functions, we assume that they are memoryless equations which satisfy that functions, and here we have all information on on memory. But what I said that we have the integral decomposition and we can proceed in two ways. In first way is I brought the right direction that we can choose any functions of h and f whose integrals give me the q function. And it is not a unique way. I can choose many functions which satisfy this. Only I need that their Laplace transform exists. And I can proceed in the right direction. So I can choose these functions and that functions, these functions or these functions, and immediately I found it that one, because it should be the memoryless functions related with this. And usually when the people are saying about subordination, they're doing the same. What it is, the subordination? In the subordination, we assume that these h functions is related with, is a density distribution functions of some parent process, and this f is a density distribution function of a leading process. And we have only integral. I will not speak here about the probabilistic interpretation. And what we need, that our function as normalized at first argument, and it is very easy to show it, and non-negativity. And moreover, what we need that the functions f related with the memory is infinitely divisible functions. And if these f functions satisfy three conditions, these three conditions, we say that it is safe probability density functions. If not three of them, only two of them, we say that it is dangerous. So with normalization, there is no other problem. With non-negativity also, because here we can use the Bernstein theorem, which uniquely connected the completely monotone functions with the non-negative functions. And what it is completely monotone functions is defined here. And our second functions looks like that, and it's related with the memory functions. Here we have k or m, and we can show it that it is positive, and this is normalized functions if we have that they are Sony pair, and if they are completely Bernstein functions. Here is a definition of these two functions. And they are infinitely divisible functions. Why we need it? Why? Because we want to satisfy that the causality property, causality law is satisfied. And this is the reason why we need it, because we play here not with the group, but with the semi-group. And we need this semi-composition property of the function for these functions J, because one is the inverse subordinator, and here we have the direct subordinator. And I know the semi-group composition property only in two cases, where we have only in three cases actually. First, when we have the exponential functions, the second Levi-stable distribution is here, and for Mittag-Leffler functions also it is known. Okay, and what we want for the integral variable xi, if we want to interpret it, it's as a map between the time and this xi. So we want that it is the Zadlak functions. So it means that xi must be non-negative, and it must be decreasing functions and uniquely determined for any time larger than 0, and must be discontinuous, but must be pairwise continuous with the left limits exist. So here are examples of the Zadlak functions. And when we have the Zadlak functions, we can say that it is the random variable, and we can relate with the subordination. Okay, and here there are some examples of Efros theory. I said you that they are not unique. So here is the Efros theorem, integral decomposition, and we can present the normal distribution, which looks like that, as a here. Normal distribution depend on xi and the memory functions subordinated by the Dirac distribution, delta Dirac distribution. And we obtained the normal distribution when we integrated. But here is a more interesting example. I'd call it court example, because we have two functions, one of them, and the second one. The second is similar to the Bessel process. But when we calculated the Laplace transform of these things, we obtained that they are related with the parabolic equation. And for the parabolic equation, we know that there don't exist any limitation of some parameter. We call it, as a physicist, for the velocity. We have infinite velocity. And these functions is related with the wave equation. So its Laplace transform is here. And we have the speed, finite value of speed. Speed is a. And these functions is related with the memory. So why we cannot use it? Because when we calculated such integral, we obtained our result. But why we cannot use it? We cannot use it because here is the hyperbolic equations hidden, and we have hidden the process with a finite speed. Velocity, and here we want to obtain the equations which is probabilistic equations. So we want the infinite value of speed, and this is the main reason why we cannot use it. So here, few words about the evolution operator approach. When we look at the book of Wieder, here, the heat equation, he showed that the solution of Fokker-Planck equation can be presented in such a way. So here we have the evolution operator, which is given by the T and Fokker-Planck operator. It can be, in the simplest version, it can be the second space derivative acting on the initial conditions. And here we have another book, Arendt book, Vector Valuable Laplace Transform and Cauchy Problems. And he considered the wave equations. And here we have the finite speed. And he presents the solution also as some evolution operator acting on the initial conditions. And here we have this evolution operator. It's a cosine operator, because we shouldn't understand it as a functions, where we have the derivative over x, and because it's the second equation in time, so we need two initial conditions, and we assume the first initial condition and the second initial conditions. And here we are taking that equals to 0 to obtain the subordination process. But from the Efros theorem, we can generalize it, these results for such equations, where we have here the memory functions and Laplace operator. And Efros theorem says us in one way that it is the normal distribution acting on some functions depend on the memory. And it is for generalized Fokker-Planck equation, first derivative. So we can present it as the action of evolution operator. I don't have, yes, as the action of evolution operator. Operator acting on initial conditions, and our evolution operator has such a form that these depend on the memory functions and the basic operator given by the reader. And similar things we can do for for the generalized wave equations, because we have here the second derivative, and it is the action of the evolution operator or initial conditions, where here initial conditions is related with the functions cosine. And what I'm doing now, it's something which is related with the telegrapher process and the Catania process. Equation is the same as I said. Here we have the second time derivative, the first time derivative in time, and second space derivative on x. What is the difference? The difference is that in telegrapher equation, the difference interpretation of tau and I, and also what it is important for us, initial conditions, that here we are assuming that we have real functions in both cases. And here we are assuming that we have only non-negative functions, such that we need to obtain the solution of these functions u, which is non-negative functions, because we want to interpret it as a probability density function. And here we don't have it. So our solution, positive solution, looks like that, and it can go to the solution of wave equation or to the solution of diffusion equations. And what was interested for me is if we know the limits of these two forms, so we should observe. You should be able to observe the wave behavior. And here is a generalized version. Maybe I will omit it. And when we have the wave behavior, one of the signal of wave behavior is a frequency shift related with Doppler effect. And with Doppler effects, what we need observer sources, and frequency shift. Just we observe the frequency shift. So here we have if we have the ambulance which is moving toward us. So here it starts to be noisy. If we are here, so we have high frequency. Here is a lower frequency. And and what my PhD students made, okay, I'm almost fine. And he calculated by using the short time Fourier transform. He observed such things that we can really observe the frequency shift. It's the time and the frequency for the telegrapher Catania-Vernot equation. And here, if we don't consider if we are very close to the diffusion equation and to the wave equation. Okay, thank you.
Questions?
A very naive question that you may explain already, but so what are the physical factors that determine whether diffusion is subdiffusion or superdiffusion?
The physical factor. Okay, super diffusion usually is because we observe it. This is the main reason. And they are relating with the behavior right now, with the behavior of some proteins, with tumor in our brain. Super diffusion is usually related with the behavior. Okay, from experiment we obtain the mean square displacement. Yeah. And if this mean square displacement is from t to nu smaller than t, we have this subdiffusion. If it is larger, we have the super diffusion. Usually we observe the subdiffusion, but in some experiments, like if somebody has the problem with the heart, and the blood don't flow fluently by the heart, and it is related with the heart attack. Before this heart attack, you can observe the superdiffusion behavior. In some chaotic system, also you observe the superdiffusive behavior. So if I answer.
Other questions? All right, let's thank Katarzyna again.
Yep.
All right, and in order to get slightly back closer to time, but still have a chance for the break, let's be back at 15:15. And then there's another discussion section at that point.